Hello everyone, this is Dr. Young here, and in this video we're going to talk about some more of these reactions at that alpha carbon, specifically the alkylations and acylations. So recall from previous videos, right, that we had the thermodynamic and the kinetic enolate, right? So the first one here over on the left, we said this is the thermodynamic, right, thermodynamic enolate. And it was the thermodynamic one because it's a more substituted alkene. More substituted alkene, which made it more stable. All right, so if you look at this alkene right here, that's more stable, right, than this one right here. And the way we got these, right, were by using a small base so that it can get into that tertiary carbon a little bit more easily, right, because that's a tertiary carbon, versus over here on the right-hand side of the carbonyl, right, the other alpha hydrogen was a primary one. It's just going to be easier to go to that primary carbon. So we need a little tiny base if we ever want to get to that tertiary one and get to that more stable enolate. So we need a small base, and we want warmer temperatures so that if there is an equilibrium, everything will end up in the lowest spot, namely this enolate. So we want sort of warmer conditions. And if I go on the right-hand side, right, we said that was the kinetic enolate. So that's the kinetic enolate. Because again, it's just faster for your base. It's easier for your base so that transition state has a lower energy for the base to come in to the primary one. The way we get the kinetic enolate, right, is by using really large bases, really large, really bulky bases like LDA. So large bases. And we want cold temperatures. We want to make it so that this reaction is kinetically controlled. So if you have a really low temperature, then activation energy is going to be the main determining factor in what your reaction mixture is going to be. So we want cold temperatures, -50, -78, stuff like that. Now, the important thing to remember here, right, and you may remember this from the previous video when we talked about the difference between these two, the key thing here is that now once you make these enolates, these are now nucleophilic. Right, both of these become good nucleophiles. Right, because they're quite basic, right? They have relatively high pKa's. Remember those pKa's of that alpha hydrogen was about 25. So they can go and attack an electrophile. And that's what this whole video is about, is two of the electrophiles that they can go attack, alkyl halides and acyl halides. So remember that for alkylations, right, alkyl groups are just, we're talking about things that are just sp3 hybridized. So things that are just plain C's and H's, alkane-like stuff. Right, that's what alkyl means, right, like an alkane. And what we're going to see for all these alpha alkylations that we have two steps. First, we need to form the enolate, which is what we talked about before, that kinetic or that thermodynamic enolate. And then we have to add an electrophile. And for alkylations, that electrophile is just going to be some sort of alkyl halide. And what we're going to do is we need an alkyl halide that can do SN2. So that means that we are really only going to be able to do methyl and primary alkyl halides, right? Because we need to do an SN2 type reaction. It's kind of like what we did with the alkynes when we had that terminal alkyne and you remove that H, and then it could go make a new CC bond. But it went SN2, so you could really only do it with methyls or primary in any sort of speedy way without having too much elimination product. So we need to add an electrophile, so it's going to be an alkyl halide like a methyl or a primary. So let's look at this first example here. All right, the idea is that I'm going to add LDA. So my step one is I have LDA. And I'll draw out this first one here. In this case, I've got a bunch of alpha hydrogens, right? I've got two alpha spots, but they're equivalent, so I'm not really too concerned about which hydrogen I'm going to take off. LDA is going to pluck off either one of those. Doesn't really matter which one. So I'll just pick this one. Now that's going to give me the enolate here. Now I have a negative there, and of course there's that resonance structure that we were talking about before, right? The whole reason why these are so stable. And what's kind of weird about these, and we don't have to go into too much detail, it's not weird. It's only weird in that, right, we said that this was the major. Whoops, come on, my friend. This is the major contributor, right? This is the minor. And so you rightly should think that, oh, well, the O minus is where the negative charge is. So the O minus is the thing that should attack that ethyl tosylate thing, right? So I got my nucleophile here, the ethyl tosylate. Line that back up. So the OTS, right? Remember, tosylate's just a great leaving group. And so if I look at my ethyl tosylate, I've got the partially negative oxygen, partially positive carbon. I've got a primary. So I said alkyl halides, but really any electrophilic thing. So like tosylates, mesylates. So you might be asking yourself, well, why doesn't the oxygen attack that partially positive carbon? Why is it going to be the carbon that attacks that carbon? Which is absolutely what we're going to see. We're going to see this carbon attack that carbon to do the SN2 reaction to give us our product. So why does that occur? Why doesn't the O attack it? And again, it has to do kind of with the hard-soft rules that we were talking about before. And it kind of has to do with like how well the orbitals overlap. So there are things that will attach to the oxygen in this enolate. It's just that alkyl halides or alkyl groups is not one of those things. We're not really going to see a carbon group go onto that O. It's not going to be very, very stable. It's going to fall back off probably anyways. It's just not very stable. There are things like silyl groups, like so silicon is really oxyphilic, and so those will definitely add up there. You can make enol ethers, but we're not going to worry about that right now. So for us, we're just going to go ahead and take that alpha thing, right, that alpha spot, and put our alkyl group in that alpha spot like we did here. Right, there's my alpha spot. Come on. And so that's all we really did, right? We had LDA to deprotonate. We added an electrophile, which was an ethyl piece. And so we added that ethyl group, and there's my product. It's the same thing for the next one, only now for the second one, I have choices. I have an alpha group on the left and the right. I have alpha hydrogens on both of them, right? I have 3 on the left, 1 on the right. I have LDA, and I want to remember, right, that LDA is the big one. So now I have to make the choice, right? If I have a giant base like LDA, is it going to go to that tertiary carbon on the right-hand side that's more crowded, or is it going to go to the primary carbon on the left-hand side where there's more space? And the answer is that the LDA, right, is definitely going to pluck off the hydrogen that is on the left-hand side because there's more space. So you're going to get the enolate where you form the negative on the left-hand side of that carbonyl. And then, right now that we have that enolate, step 2 is we just add in this benzyl bromide methoxy thing that we've got going on. And this is just going to attack that secondary, or attack that primary carbon, kick off the bromine. And now we've got our new molecule. Right, so it's just an SN2 type reaction. So now I'm going to redraw the parent carbonyl. Here's that alpha carbon that I deprotonated from, and I'm just going to attach it to, so that's the 1 carbon hanging off, and then I had an aromatic ring. And it looks like meta to that was a methoxy. Right, so this right here, that was the new bond. Right, because this carbon right here where the bromine is this carbon right here that just got attacked by my negative enolate. So I just kind of redrew the whole thing next to it, is the idea. But you can add on whatever alkyl group you want, whatever really good SN2 substrate you really want, and it'll just add to that alpha spot. And so in this last one right here, I have another ketone. It looks like I got a little more complicated here, right? So I'm going to draw my alpha and my beta here. Sorry, my alphas. So alpha, alpha. So it looks like to me, this is the new thing. That's right, that's the new bond for this one. So I just need to add, right? The thing that I need to add here just needs to be this with a good leaving group, right? That's the good SN2 substrate that I need to add. It just needs that, and I'll just slap on a good leaving group. Also, I noticed in this one that, again, I took off the less substituted. I took off the alpha hydrogen on the right-hand side, so again, it looks like I wanted a kinetic one, kinetic enolate. So what I'm going to write for reagents here is I'm going to write that I need LDA. Again, I would just write that it's probably cold. These other ones didn't say that it was cold. And then for number 2, it looks like I need to add, right, I had this whole piece. This is the carbon I said is going to form the new bond. So I'm just going to put on a leaving group on here. I'll just put on bromine. I'll just put bromine on there so that I get all of the carbons that I want, right? Because it looks like I needed 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. So I've got them all. That'd be the reagents that I'd want to use. Now, in these examples, I didn't have any of a small base to go to the other side. I probably should have. In fact, let me see if I can just add one for you. Here, let's just add one example of where you use a small base to alkylate something. Right, so let's say instead I had NaNH2, and then in the second step we added this 1, 2, 3, 4, 5, this pentyl iodide, or 1-iodopentane. Right, again, so now the idea here is this is a small base, so it's going to go kinetic, or in other words, the more substituted one, right? So if I look here and here, it looks like that's my more substituted spot. That's the H that we're going to take off, right? Because it's small, so the difference in those transition states is not as big. These are reversible acid-base reactions. So it's going to end up stabilizing with the thermodynamic enolate. And then, like we said, in the second step here, this is just going to do your SN2 reaction to give us our product. So I added 1, 2, 3, 4, 5, and I have one more hydrogen there. Sorry, that last one got a little away from me. There we go. So that would be the product in this one, right? Where I just alkylated in that, I just alkylated and added that 5-carbon piece there. So there's an example of doing a alkylation on the thermodynamic enolate. So let's look at alpha acylations, right? So just like with the Friedel-Crafts alkylations versus acylations, that acyl group, right, just means you start with a carbonyl. So the group starts with a carbonyl, right? So for example, this would be considered an acyl group. I'm drawing the squiggly line just to mean that, it's attached to something, who knows what. But an acyl group starts with the carbonyl is the idea. And to do alpha acylations, it's the same 2 steps. You form an enolate with a strong base. I'll just write strong base here. And then you add an electrophile, which is going to be something that we call an acyl halide. And acyl halides, an example of acyl halide would just be, you instead of an alkyl halide where you have just sp3 hybridized things, now it just starts with an acyl group. So I have an oxygen with the chlorine attached to that carbonyl, or a bromine, or something like that, so that it's a good leaving group. And if we look at the mechanism down here, I'll do this first one. It's going to be really, 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 really similar to the alkylations. There's not that big of a difference. Right, so I've got my big old LDA friend. I'm going to have it pluck off one of these hydrogens, which allows me to form my enolate. Now, the difference with this is that, so in this case, I just have a 3-carbon acyl chloride. 1, 2, 3, yep, there we go. Now, the difference here is just going to be that my enolate, right, if you look at these acyl halides, and I'll talk more about these types of reactions, these additional elimination reactions in a future video, but a real quick primer on them is if you look at these, right, you put your partial charges on the molecule, obviously the negative carbon is going to be attracted to the partially positive carbonyl carbon. And you might think that the chloride just kicks out at this point, but really the weakest bond on here is that pi bond, so it actually kicks up and breaks the pi bond, kind of like if you were adding something to an aldehyde or ketone. Now, the interesting thing here is that you've got an O minus, you've got a Cl, and now you're attached to the alpha position. Now, the O minus is not super happy, an O being negative is not bad, but a chloride being negative is better, so we're not actually at our lowest energy intermediate or reaction set yet. And so these electrons can drop down and kick out this really nice leaving group, chloride. And what we end up getting then is it looks like we just basically added the acyl group to that alpha spot, right? We said, here is my alpha spot. Here's the alpha spot we were talking about. If I look at the acyl group that we wanted to add, right? This was the acyl group that we wanted to add. And that is exactly the group that I just added to that alpha spot. So you just need to add the acyl piece, right? Ignore the chlorine or bromine or whatever's in that attached there. And you just attach that to the alpha place, right? Because that's where your enolate's going to attack and eventually kick out that chloride. And so now you've made a new carbon-carbon bond. Let's look at a second example here. Here I have a small base. So I'm going to go for the alpha hydrogen to make the thermodynamic enolate, which will be on the right-hand side. If I draw what that looks like, we're going to get the anion here. And in the second step, right, we said our enolate is going to attack the carbonyl carbon. I'm just going to draw these together for now because I don't want to make this a whole mechanistic thing. And then the electrons, right, we'd have that intermediate, and then they're eventually going to drop back down and kick out the chloride, right? That doesn't happen in all one step, it's two steps, but I'm just going to squish it together. So that then we get this sucker. It's a terrible pentane, but you know what I'm saying. So again, I just took that group that was the acyl halide, and I just attached it to the alpha spot that I deprotonated from. That's really it, hence an acylation. And so it'll be the same thing in this last one, right? I've got two alpha carbons. I see that the thing that I'm adding at the alpha carbon on the right-hand side is this. And so I need to pluck off the alpha hydrogen on the right-hand side, which I notice is going to leave me with the kinetic enolate. So I'm going to use something big and strong like LDA and low temperatures so that I go off to the right-hand side. So I get the kinetic one. And then for step 2, I'm going to add the piece that I want, which is this isopropyl acyl piece. I'm just going to slap on a halogen. Chlorine is really the most common one that you're going to see because it's easy to make with SOCl2. But it could be a bromine, it could be a lot of things. It could be an anhydride. But this would be a set of reagents that should give me that product, is the idea. So I want to give you just one example, one synthesis example. See if you can use this to make the following compound on the right-hand side, thinking, of course, of doing an alpha alkylation or acylation. I want you to take a pause, see what you can do. Multiple steps. It's going to take multiple steps and multiple reagents. So coming back to this, what I'm noticing here, right, if I take a look at the molecule on the right, one of the things I notice is that I have a new CC bond, which is an important thing to notice, right? I've gained carbons here, so I have a new CC bond, namely this one right here. And I'm also noticing that that CC bond showed up at what was my alpha carbon, right? So I have a new CC bond at where I used to have an alpha carbon, which is making me think, you know, that's a way that I could turn that into an enolate and then attack that other piece, that new piece that's on there. Another thing that I'm noticing is that it looks like I reduced my carbonyl. I reduced the carbonyl. And at first when I looked at this, I thought, ooh, this is Grignard for sure. But then I realized that I would have had an extra methyl on there, right? If I tried to attack that acetophenone, that thing on the left, that phenyl methyl ketone, I would have ended up with an extra carbon instead of an H where I have the alcohol. So I don't think it's a Grignard reagent. I think I need to use this alpha thing. And so what I'm going to do is I'm going to go ahead and I'm going to pluck off the hydrogen from that alpha carbon. This will be my first step. So one, I'll use LDA so that I can make my enolate. All right, that's going to give me this enolate. So that's my step one. Again, it's the carbon that acts as the nucleophile for whatever the thing is I'm going to add. I see that I need to add this piece. So 1, 2, 3 carbon piece. So I need to add basically this, and I need to slap on a leaving group. So I'll just use bromine because I know that's a nice good leaving group. So that'll be my second step, right? And I know that in that step, basically this is going to just do an SN2 reaction to give me this. All right, so actually let me erase it. I'll make it green just so we can see it extra well. Right, where the purple is that new bond that I was talking about, and the green is that new 3 carbons that I added at the alpha spot. And I'm not quite there yet. I know I need to reduce this. We can do reductions in a couple of ways with sodium borotetrahydride, lithium aluminum tetrahydride, or H2 and palladium. I'm not going to use H2 and palladium because I don't want to reduce my alkene. So I'll use something as mild as possible. So I'm going to choose the sodium borohydride, just because I know that's super mild and it only works with ketones and aldehydes. So NaBH4. And then that would be the 3 steps. If I want to turn that first molecule, that really cheap, easily, readily available acetophenone, into a more complicated molecule, this is how I'd use alpha alkylation in this case to make that. So I hope that gets you going. Do lots of practice. Good luck studying. Take care.